Okay, so suppose we've got a real finite dimensional vector space V and a linear map J from B to B, which squares to minus the identity. So here's a nice little demo. In that situation, we can find a basis for our vector space V of the form E1, F1, E2, F2, dot, 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 En, Fn, where J will send the E's into the F's, and J will send the F's into minus the E's. Sort of prove it by induction, right? But exercise prove this, all right? So in particular, this means that the dimension of B is going to have to be even, see, because there's an even amount of vectors in the basis. So if your vector space is going to support a linear operator which squares to minus the identity, then it's going to have to be even. Okay, so now let's try and understand the eigenvectors of J. So first of all, what are the eigenvalues? Since J squares to minus the identity, that means the eigenvalues are going to be plus minus I. And that means that its eigenvectors are not living inside V itself, but the complexification of V, right? In other words, we extend J to a complex linear map in the way we talked about just now, and then we're going to decompose the complexification of V into the eigenspaces of this linear map here. So let's calculate these eigenspaces. So what, for example, are the eigenvectors with eigenvalue plus I? So if I want J to act on a vector in the complexification and return I times that vector, what do I need? Well, J acts on this vector in this way, by definition. And I times this vector is this, by definition. So that means I'm going to need that this is going to have to equal this. And this is going to have to equal, so JV2 is going to have to equal V1, which both of those conditions are saying the same thing, namely that V2, that vector there, must equal minus J times the first vector V1. In other words, the eigenspace of the J operator with eigenvalue I, which I'm going to write as V superscript 1, 0, consists of all vectors of this form in the complexification. So it's where the second component of the complexification is minus J times the first component. Okay, and similarly, the eigenvectors with eigenvalue minus I are going to look like this. So we've decomposed our original vector space V, or at least its complexification, into two subspaces, the 1, 0 subspace and the 0, 1 subspace, which look like this. Okay, if you want to find a basis for them, remember that our original real vector space V had this basis, meaning that the complexification had the same basis. And now a basis for this space would then be, I can put these V's equal to the EI's. J times the EI's are the FI's. So V minus IJV is EI minus IFI. And I don't need to do that for the F's because then it should just be I times the previous one. You know what I'm saying? So, so I only need to do vectors of this form. So these are, call these AI's, and there's going to be M of them, right? So these are going to be a basis for the plus I eigenspace, and the minus I eigenspace are going to have this basis here, which I call the A bar i's, because I've taken the complex conjugate of these vectors to give these vectors. Okay. So note that we have an antilinear bijection between these two eigenspaces. Namely, I can send a vector W to a complex conjugate. So it's not a linear map, but it is an antilinear map, and that's fine. All right, so it's something to bear in mind. You can translate from the one subspace to the other. Okay, so given a real 2n dimensional vector space, we have its complexification, which is a 2n dimensional complex vector space. Given a real 2n dimensional vector space V and a linear map from the vector space to itself with squares to minus the identity, we can decompose the complexification of V into the plus minus I eigenspaces of J. Okay, but there's a third thing. Given a real vector space and a linear map on it, which squares to minus the identity, we can also regard this real vector space V, which was a 2n-dimensional real vector space, as an n-dimensional complex vector space. So instead of complexifying it, take that same underlying set V and think of it as a complex vector space. In order to do that, I have to tell you how to multiply with complex scalars. And in order to do that, I have to tell you how to multiply with the number I. And I just define I times a vector V to be JV. You see, that makes sense because I squared is supposed to be -1 and J squared is minus the identity. So I squared will act as -1. Okay, so keep this in mind. That's so that you can always regard a real vector space with a complex structure as a complex vector space. Okay. Now, let us do some more linear algebra here. So let's talk about joules. Let me give some, go to this page here. So right now I've started this V and I've decomposed the complexification of V into the 1, 0 eigenspace and the 0, 1 eigenspace. Now what I want to understand is the dual space of V, right? What do I mean by that? I just mean Homs from this vector space to the complex numbers, right? This is a complex vector space. I mean complex linear Homs. So what is the dual space? Well, since the original vector space decomposed, the dual space is also going to decompose, right? And we can decompose it like this. So I'm going to write it as a direct sum as well. I'm going to write it as B star 1, 0 plus B star 0, 1. I'll put a little C there if you like. Okay. And this guy here is simply the dual of this subspace, and this guy here is simply the dual of this subspace. But as maps from the big space, these guys are just the maps which are 0 on that component. And these guys are just the maps which are 0 on that component. All right? So let's just be clear that this guy is the same as the set of all linear maps from VC into the complex numbers, such that F is equal to 0 on vectors that's living inside V01. And similarly for this guy here. Okay. That's a short way to go about it. Now, what do I need when I'm talking about manifolds? I also need to, so I've got this dual space, and remember, we want the exterior algebra, so we need the powers of the dual space. So let's think about that. So when I'm doing manifolds, I'm interested in these exterior powers. So I want to take the dual space, and I want to take its kth exterior power. So that means I'm taking the kth exterior power of a vector space, which is a direct sum. And if you take the kth exterior power of a direct sum, then that's going to split in the following way, as you'll agree. I'm going to split it as a sum like this. We take two indices A and B, which add up to K. And then I'm going to take the A, 0 exterior power of B star tensor the 0, B exterior power of B star. Right? What does this here mean? This just means I take the 8th exterior power of this guy here. And this here means I take the bth exterior power of this vector space here. And I take those two and I tensor them together, and that would then be the kth exterior power of this vector space, right? So that's just a complicated way of saying that if my vector space V is the direct sum of two vector spaces A and B, then the kth exterior power of V is going to, if you just calculate it, it's going to be sum all A plus B equals K of the 8th exterior power of A tensor the bth exterior power of B. Okay, that's just saying that I take a wedge, that's the things that are wedges of K vectors. It's going to consist of, I have to make wedges of K vectors out of A and B. So I could take A of the wedges from A and B of the wedges from B, as long as A plus B adds up to K. Okay. So this thing here, vectors of this form, where I've got A wedges from first guy and B wedges from the second guy, I'm going to call that lambda A comma B, B star. Okay. So if this equation here holds on any vector space, that means it will hold on the tangent spaces of a complex manifold, right? And so because, yeah, and so that means it's going to hold on the, right, because a complex manifold or even an almost complex manifold has this map J, right? So if M is an almost complex manifold, that means that each tangent space TPM has this J operator, which squares to the identity, right? So that means that on the cotangent space, I can form the cotangent space at P, that's this thing. I can tensor it with C to make its complexification. And once again, this is going to split into a direct sum of two subspaces. The 1, 0 eigenspace, right, like that. And the 0, 1 eigenspace. Okay. And so that happens on each tangent space. Right? So once again, here's a point P in the manifold. Then I've got the tangent space at P. That I've also got the dual of the tangent space at P, which is this guy. I complexify it, and I split that complexification as a direct sum of two subspaces. And then I can talk about the kth exterior power of that guy. And the kth exterior power is then going to split up as a direct sum like this. All right. So that since this holds on each and every tangent space, that means it's also going to hold on the tangent bundle. Okay. In other words, this breakdown here is going to hold on the tangent bundle and hence on sections of the tangent bundle. In other words, K forms on M, complex valued K forms on M, is going to split as the sum of K forms of type A comma B. Okay. Now you might not be following me at this point. Maybe you got lost. So let's just go through what am I saying here. Okay, so let's dumb all this down and get right down to the basics. Okay, so let's have a look. Locally, in a chart, what am I saying? I'm saying I've got my manifold M. So this is the thing I want to understand, that every complex manifold, in fact, every almost complex manifold, the K forms decomposes as this in this way. So let's understand this. So M is a complex manifold. So I've got a point P, and I've got an open set around it. And I've got these coordinates, right? Z1 up to Zm. These are holomorphic coordinates on that chart. Now, each of these Z's I can write as X plus IY, obviously. So now I've got two M-dimensional real coordinates on M. Okay, so that means that del X1, del Y1, comma, dot, 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 comma, del XM, comma, del YM is going to be a basis for the tangent space at M, right? Basis for this tangent space here. And notice that this basis is exactly of the form that I was speaking about earlier, where if I apply J to this vector, then I get this vector. And if I apply J to this vector, I get minus this vector. Right, let's have a look at that. Because J on del xi is del yi, and J on del yi is minus del xi. Okay, so all good. Where are we going next? So now I want to make these AI basis vectors, which before, remember, I said you can form these basis vectors here for the 1, 0 eigenspace and the 0, 1 eigenspace. I call them AIs. And yeah, I'm going to make a slight difference. I'm going to just multiply them by a half. And you'll see why in a second. Okay, so I'll call those del ZIs. I'll say del ZI by definition. It's not some geometric thing. It's just a formal thing. It just means a half of del xi minus I del yi. And it's a formal vector living inside the complexification of the tangent space at P. And similarly, I've got this guy here. Which is, maybe I should write it like this. It's the same thing, but I'll just write it like that. So that's del xi plus I del yi. And that's also living in the tangent space at C. And actually, it's not just in the tangent space. It's in a certain component of the tangent space, right? This guy is in the 1, 0 component. And this guy is in the 0, 1 component. And each of these, this is a subspaces of the complexified tangent space. Okay, and the cool thing about them is that they are eigenvectors of the J map. Okay. Good. So we've got a basis for this complexified tangent space, right? It's all the Z's, the del Z, sorry, and all the del Z bars. Just like these A's were a basis for this, for the 1, 0 part, and the A bars were the basis for the 0, 1 part. That's all I'm doing. I'm just doing it at the when V is the tangent space of a manifold, of a complex manifold. Okay. So since I've got a basis for a vector space, that means I'm going to get a basis for its dual. Let's call it, we have a dual basis. For the cotangent space, right? And now, if you will just be happy with me for a second, I'm just going to call that D. So, okay, so hold on. I'm going to call this DZ1, dot, 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 DZM. and then dz bar 1, comma, dot, 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 comma, dz bar m. Okay. And I notice, so what is the definition of these guys? This guy eats that guy to give 1, and all the rest give 0, and so on. Okay. And you notice that dzi is equal to dxi plus dyi, I dyi. And dci bar is dxi minus I dyi. What do I mean by that? If I take this guy, if I take this thing here, which is clearly a vector in the complexification of the dual space, and I eat up, say, this vector here, I feed it this vector here, what would it mean to feed it that vector there? If I were to feed it this vector, by definition, this vector is this vector here. So let's act on that vector. What will happen? So the half comes out in front. Then the dx is going to eat up the del xi to give me a 1. And then it's going to eat up the del yi to give a 0. The dy is going to eat the del x to give you a 0, and it's going to eat the del y to give you a 1. And I've got an I times a minus I gives you another 1. So I get 1 plus 1. That's why I needed the half, right? So where are we? We understand that we've got this basis for the complexified tangent space and has this, and this is a nice basis because these guys are the eigenvectors of J with eigenvalue I. These guys are the eigenvectors of J with eigenvalue minus I. This has a corresponding dual basis for the complexified dual tangent space. And we write them as the DZs and the DZ bars. Okay, and these guys are going to be a basis for the 1, 0 parts of the cotangent space. And these guys are basis for the 0, 1 parts of the cotangent space. Okay, so that means, for example, what is a basis for the second exterior power of the cotangent space, the complexified cotangent space? Well, this complexified cotangent space, with this second exterior power, we agreed, can be written as a direct sum of 3 subspaces: the 2, 0 subspace with the 1, 1 subspace with the 0, 2 subspace. See, the point is that these numbers here must add up to this number here, which is 2. And what do I mean by this? I just mean a basis for this space would be things that you get from wedging the DZs together. So wedging things in the T1 naught together. So I could form here DZI wedge DZJ and so on. Right? Things over here I would get from wedging a DZ with a DZ bar. And over here is where I would take just wedges of DZ bars together. Okay, so let's be clear. Let's say M is 4-dimensional, 4 real dimensional. So it's 2 complex dimensional. Okay, so that means that the cotangent space complexified is going to have a basis consisting of dz1, dz2. Those are going to be the 1, 0 basis. And then you got the dz bar 1 and the dz bar 2. Okay. The second exterior power of the cotangent space is going to have a basis that's going to split up as follows. Well, let me first of all write this like this. So this guy splits it as a direct sum of the 1, 0 part and the 0, 1 part. And these guys were a basis for the 1, 0. And these guys are a basis for the 0, 1 sector. Okay. So similarly, let's talk about the second exterior power. It's going to split up as the 2, 0 sector. I'll stop writing the TP star M's, and it's going to have a 1, 1 sector, and it's going to have the 0, 2 sector. And a basis for this is going to be things that you can form by wedging the DZs together. So you can't, for example, do DZ1 wedge DZ1 because that's going to be 0. So the only thing you can form is DZ1 wedge DZ2. Over here, what can you get? You can do a DZ1 wedge DZ bar 1. That's okay now because these things are different, you see. You can do a DZ1 wedge a DZ bar 2. You can do a DZ2 wedge DZ bar 1, and you can do a DZ2 wedge DZ bar 2. And over here, you have to wedge the DZ bars together, so the only thing you can do is this. Okay, so notice, if I count them all together, I get 1, 4, and 1, so it's 6-dimensional, which makes sense, because if I've got a 4-dimensional vector space and I consider it second exterior power, then it's going to be a 6-dimensional space. And I've split up that 6-dimensional space like this now. What about the third exterior power? Okay, so now this is going to split as the 3, 0 part, the 2, 1 part, 1, 2 part, and the 0, 3 part. A basis for this, let's think about it. I have to wedge DZs together, and I can't do it 3 times. Right? So there's nothing here. Over here, I have got to do 2 of the DZs. So I can do that, DZ1 wedge DZ2, that's the best I can do. And then I'm going to have 1 of the DZ bars. So I can do a DZ1 bar, or I could do a DZ2 bar. Okay. Similarly, over here, I need to have 1 of the DZs, and then I have to have 2 of the Z bars. So these are the 2 possibilities. And this guy here is 0. Okay, so all in all, I've got 2 here, 2 dimensions here, 2 dimensions here. So it's 4 dimensions, which makes sense because I've got a 4-dimensional vector space. So its third exterior power is going to be 4-dimensional because you're basically just leaving out one of the basis vectors each time. And finally, the top exterior power of a 4-dimensional real manifold, which is in our case is a 2-dimensional complex manifold. So the top exterior power is 4th exterior power. And it's going to split up as, well, a bunch of things that are 0. These are all going to be 0. Sorry, 3, 1. 2, 2 is not 0. 1, 3 is going to be 0, and 0, 4 is 0. So all of these are 0, 0. This is a 1-dimensional space, and it's going to have a basis given by DZ1 wedge DZ2 wedge dz, bar 1, wedge dz, bar 2. This is a zero-dimensional space. This is a zero-dimensional space. Okay, so I hope you have now understood very clearly how the forms on a complex manifold, or even a almost complex manifold, that's all I needed. I just needed this J structure split in this canonical way into a direct sum of their what we call holomorphic and anti-holomorphic parts, which is a bit of a misnomer. It would be best to just call it a decomposition of forms on an almost complex manifold. Okay, I've shown how the cotangent space is split up. So a form is just things that look, you have coefficients in front of this that are now arbitrary smooth functions, right? So e.g. a 3 form on our complex manifold M looks like locally in this chart. I can write it. Remember, these are bases for the form, so I can write it like this. It's going to be, let's call it omega. So it's going to be some function times this guy plus another function. Let's call that function f1. And I've got another function f2. And then I've got another function f3 times this guy here. And another function in front here. Now these functions that are in front, they are not necessarily holomorphic at all. They're just arbitrary smooth functions, right? So I can write them as f1, which is a function really of the underlying smooth variables, which is x1, x2, y1, and y2. I can also think of it as function of z1, z2, z1 bar, and z2 bar. But the important point is that there's no condition on them, right? They just have to be smooth functions. So smooth linear combinations of these basis vectors locally, that's what a 3 form is going to decompose as on a almost complex manifold. So I hope you understand now this very important decomposition of forms on an almost complex manifold.